This video is going to be a crash course in linear algebra. Obviously, we're going to have to cut some corners. An introductory linear algebra course takes a full semester, and we're going to try to get through this in 10 or 15 minutes. So what we'll cover is matrices, what is a matrix, vectors, what is a vector, and some of the operations that you can perform on those things. So our goal is to get to the point where we can look at an expression written in matrix format and understand what's being expressed. And maybe even, if we have a particular problem, be able to express that problem in this matrix format. So what we won't get to is how to solve those problems, right? All of the kind of algebraic manipulations, all of the tricks that you learn in a linear algebra course to solve problems using linear algebra. Now, the good news is that actually computers are great at that. So a lot of what you would learn in an introductory linear algebra course to do by hand, computers do brilliantly well. Which is not to say that you shouldn't take that linear algebra course. I think everyone watching this video should, if they haven't. Right? You can use those tools more effectively if you understand what they're doing. So let's get started. Here are the players. We're going to be working with matrices. So from our computer science perspective, a matrix is just a two-dimensional array of numbers, something like this. We'll usually denote a matrix using an uppercase letter. Matrices have to be rectangular, but they can be any shape, so they have some number of rows, some number of columns. This matrix here has 2 rows and 2 columns. This notation is pretty common, right? This matrix is named capital A. And if we want to talk about the individual entries in the matrix, we'll sort of name them lowercase a, and then we'll use these numbers here to indicate their position in that matrix, right? So this is row 0. This is row 1. This is column 0, column 1, column 2, which makes this value a sub 1, 2, because it's in row 1, column 2. So that's a matrix. There's a special kind of matrix called a vector, which is just a matrix that has either one row or one column. So most commonly we'll work with column vectors, which is just a matrix that has some number of rows and exactly one column. So here's an example of a column vector. We could have a row vector as well that would have only one row and some number of columns. So what can we do with these things? Sort of an arbitrary starting point. One operation that we can perform on matrices, and of course vectors are just a particular kind of matrix, is the transpose operation. So if I have a matrix A and I apply this transpose operator, that swaps the rows and the columns, right? So this row here, the first row became the first column, the second row became the second column. The transpose operator transforms a column vector into a row vector. Great, that's all there is to that. So a lot of some of our mathematical operators work maybe as you would expect. So I can add two matrices together or subtract two matrices just by adding the corresponding elements, right? So this value in the upper left-hand corner is the sum of the values in the upper left-hand corner of the two operands here. And similarly with subtraction. So obviously this just doesn't work out if these two matrices don't have the same shape. So the addition operator isn't defined for arbitrary pairs of matrices. They have to line up correctly. Scalar multiplication, right? So if we have a number, right? This isn't a matrix, it's not a vector, it's just a number. We'll call that a scalar. I can multiply a scalar times a matrix, and it's this element-wise multiplication. So every value in the matrix is multiplied by e in this example. So this is where things get interesting and complicated. So multiplying a matrix by a matrix give ourselves some room here. What's the best way to think of this? So the first thing to notice is that just like with adding matrices, there are restrictions on the shapes of matrices that can be multiplied together, but the restriction is a little bit different. The restriction here is that the inner dimensions of the two matrices have to match. So if I have a matrix with 2 rows and 3 columns, that's what this guy has, I can multiply that by a matrix with 3 rows and 2 columns, or 3 rows and 7 columns. As long as these two dimensions match, the operation is going to work out. And how does it work? We can think of it as grabbing this first row from this matrix and multiplying it by the first column from this matrix. And I multiply it in an element by element fashion, and I add all of those results together. So this is A times P, right? A times P, B times R, B times R, and C times T, C times T. And that sum becomes the value of the upper left-hand corner of the resulting matrix. So I'll perform that same operation for every column in this second matrix. So I'll now multiply A times Q, B times S, C times U, add those things together, and I end up with this sum. So I end up with one entry in this 0th row of the resulting matrix for every column in this second matrix here. And every entry in that top row is the result of working with this first row here. So this row here comes from this row here. And the second row is going to be calculated in the same way. So once I start with this row, I take this row, I multiply it by this column using this element-wise multiplication. So P times D, D times B, E times R, F times T, etc. So that's it. That's all there is to it. And right, this is just making that point that it doesn't always work. Right here, if I tried to grab this first row and multiply it by this first column, that just doesn't make sense. They don't line up correctly. Maybe this is as good a time as any to stop and think about what all of this actually means, right? This seems like a fairly arbitrary kind of operation to invent. So why is linear algebra a good thing? Well, it turns out to be a really convenient way to express operations that involve lots and lots of values. In how we interpret these matrices really depends on our application, right? So it's exactly like normal algebra. You can have some formula in normal algebra, like, 3x plus 7 equals 2. And, what does x mean here? Well, that's completely dependent on the problem that you're trying to solve, right? Linear algebra is the same. How we interpret these numbers is completely dependent on what we want to do with them. So sometimes this turns out to be a convenient kind of operation to perform depending on the problem that we want to solve. Frequently, there's a sort of geometric interpretation in mind, right? So in particular, when you're talking about a vector, let's say we have a two-dimensional vector, 3, 2, something like that. There's a nice natural geometric interpretation of that. I can think of it as a point in a two-dimensional space, right? Maybe I'll say this is my x dimension, this is my y dimension. So if this is 3 and this is 2, I can think of this vector as mapping to this point in this space. So it's called a vector, and typically I won't think of it as a point. I'll often think of it as an arrow starting at the origin and ending at that point. So if we have this geometric interpretation in mind, then these matrix operations, we can think of them as sort of performing transformations on this point, moving this point around. So for a simple example, let's say I have the matrix 2, 2, 0, 0, and I multiply that by my vector 3, 2. Now notice this multiplication is going to go through, right? So this is a 2 by 2. This is a 2 by 1. Those inner dimensions agree, so everything is going to be hunky-dory. And the resulting matrix is going to be, the size of the resulting matrix is going to be determined by the outer dimensions, right? So we're going to get a 2 by 1 matrix as the result. So let's see if that's what happens. Well, this first entry is 2 times 3. 2 times 3 plus 0 times 3. This next entry is going to be 0 times 3 plus 2 times 2. And I think the result there is 6, 4. So we started with this vector 3, 2. We ended up with this vector 6, 4, which is exactly twice, right? So this matrix doubles the length of any vector that we multiply it by, right? So it had the effect of turning this vector into this vector. Great. And it turns out that if we're clever about picking the entries in this matrix, we can do all kinds of transformations, or a large family of transformations on that point. We can pick a particular matrix that would cause that vector to rotate. If I had chosen this to be a negative number, right, that would have caused this to be negative 6, and I would have not only changed the length of that vector, but I would have flipped it around the y-axis. So I guess this is the kind of thing that you would spend some time working on in a linear algebra course. I just want to give you a taste of the way we might think about what these values mean. And notice I'm working with a two-dimensional vector here, a point in a two-dimensional space, right? There's nothing that stops me from making this, right, a three-dimensional vector, and then I can draw those too. I can draw my nice three-dimensional coordinate system, and I can, put that point somewhere in that coordinate system. And there's nothing that stops me from working with 12-dimensional vectors. I can't draw them anymore as points in space. I can still think of them abstractly as points in space, and all of the same algebraic manipulations work, right? So from the point of view of the operations that we're looking at, we don't care what the dimensionality of the space is. We don't care what the dimensionality of the vectors are. The math is going to look exactly the same way in any case. Well, we're almost there. It's worthwhile to think about a couple of special matrices, or maybe just one. So this is the identity matrix. Notice that it has 1s on the diagonal. And the only thing that's special about this is that this is a matrix that has the property that if you multiply it by any other matrix, you get that same matrix out. Of course, you have to choose this identity matrix to have the correct shape. But as long as you do that, this is a matrix that matrix multiplication doesn't change when you multiply it by some other matrix. So here's an example. I'll let you take a minute to work through that. Here's multiplying this 3 by 3 identity matrix with this vector, and sure enough, you get exactly the same vector as the result. Well, why is that interesting? Well, one reason it's interesting is that it's going to give us a notion of, loosely speaking, a notion of division for linear algebra. Right? We've seen addition, we've seen subtraction, we've seen multiplication. We don't really have division yet, and division is important, right? If you were presented this equation in the world of normal algebra, right, you would solve it by dividing both sides by a, as is expressed here. And of course, multiplying both sides by a is the same as dividing both sides by a is the same as multiplying both sides by 1 over a, and we can also write that as multiplying both sides by a to the negative 1. So what we want is this analog of a to the negative 1, the inverse of a, for linear algebra, for matrices. And just like, right, if I have a number, 3 times 1 over 3, I get 1. we're going to define the matrix inverse in pretty much the same way, except instead of 1, right, we're going to be interested in I. So a matrix inverse is a matrix that we can multiply by some other matrix that when we multiply them together, we get the identity matrix out. So how does that correspond to a notion of a division? Well, it doesn't exactly, but it gives us that same effect. So let's think about, now let's recognize that, in fact, this is a matrix. This is some vector. This is some other vector. So we're multiplying a matrix times a vector. We're getting some vector out. And we'll assume that this x vector is unknown and we want to solve for it. So with this notion of a matrix inverse, we can do that. If I have that matrix inverse, I can multiply it by both sides of my equation. I've switched things around here, so now the inverse is being multiplied on the left. It turns out to work out either way. So the matrix inverse times the matrix gives me this identity matrix. And of course, the identity matrix times a vector just gives me that same vector out. So I've then solved this equation. So multiplying both sides by this inverse matrix is sort of like dividing both sides by the same value. And this becomes my solution. So the bad news is, right, if I want to know the inverse of a numerical value, I just divide it by 1 and I get the inverse. Finding the inverse of a particular matrix is not that straightforward. And if you were taking a linear algebra course, that's one of the things that you'd spend time learning how to do. And again, the good news is that computers are fantastic at it. So, when we start looking at implementing some of this stuff in Python, that's going to be one Python instruction to find the inverse of a matrix. It's a fairly computationally intensive operation, so if you want to find the inverse of a matrix that's got tens of thousands of entries, it might take a little while.